next 90 minutes.
Thank you. So the plan of my lectures is the following. I will discuss in some detail what are the natural Hamiltonians that we have in superconducting circuits, which can be used for simulation of some reasonable physical properties of not physical, even problems. So that it doesn't make any sense to discuss the physical problems before we know what we have naturally in our system and what is this. I emphasize the word natural because if you want to simulate something unnatural, then the overhead is such that it's practically impossible. So, as a epigraph to what we have, I would like to quote all the king's men. The quote is, you have to make good out of the bad, because it's all that you have got to make it out of. So that's what we discussed. Natural Hamiltonians are quite bad in the sense that the system that we deal with is far from being ideal. So the first thing that you should realize is that nominally, when you look at what we have, the quality factor of our qubits is enormous. So quality factor, as you, I hope, know, is always defined as the product of the coherence time, whatever it is, T1 or T2, times the frequency of the oscillator, qubit, you name it. So this quality factor nominally is very good. It is for a good, it can easily reach, not easily, but it can reach 10 to 7. You will think that this is a very decent number, right? So that the qubit lives very long compared to its frequency. And of course, well, as you might have heard, people often discuss the performance of the qubits just quoting the relaxation times, but it's very misleading. The relaxation time by itself means nothing. It is really a relaxation time in the units of natural, in some sort of natural units. So why nevertheless I said that they are not so good, the qubits, that this number, which seems to be very impressive, is not so good. By the way, I should tell that the best number known to humanity for the so best number for the quality factor of any resonator whatsoever, qubit, not qubit, is about 1 billion. So it's not that far, and it's a big resonator, so that which is used for completely different purposes. So the reason why the quality factor for these big resonators is so good is basically that it's vacuum, there's nothing. So quality factor is very decent, and nevertheless, it's not so good. So now let me explain you why. So the reason for that is that our qubits are transmons. And what is transmon? Transmon is nothing but slightly nonlinear, weakly nonlinear oscillator. And it is this slightly which is so bad. Because you see, as you probably realize, if it was a linear oscillator, then you could not do anything with it. If any linear problem is trivial by definition. So it is slight nonlinearity which makes it possible to do anything non-trivial. And the fact that it's slight means that we have to compare, in fact, not the lifetime of the qubit with the frequency of the qubit. It's meaningless. We have to compare it with this small nonlinearity. And we immediately lose 2 orders of magnitude by doing that. Just got it. So how it works is that the Hamiltonian, which describes the individual transmon, is just the Johnson energy, which is cosine of the phase, plus the I will write it in the usual convention, plus the charging energy of this transmon. C is, of course, 2e squared divided by the capacitance. Now we can, for small oscillations, we expand cosine, and this thing is, of course, nothing but minus ej over 2 phi squared, well, plus minus 1/12 phi fourths and higher order terms. So it is this term which makes any computation possible. Now, if you say that this is a small perturbation, then the energy of the dominant frequency of the transmon is square root of 2Ec Ej, just nothing but harmonic oscillator, and then that's it. Yeah, sure.
So physically we're talking now about Josephson function.
Yes, so maybe I should draw sort of schematics, right? Let me draw it so that it's exactly the correct question. That's our whole device. We have capacitance and the Josephson junction. And in reality, if you are curious, let me draw the schematics how it sort of looks physically. It's something like that. We have, well, I will be sort of so, and then so this is a big capacitor pads, right? And then there are 2 little wires which I call whiskers, which overlap here, so like that. So that's your Josephson junction. Yeah.
You mean they're connected only with one side?
Sorry.
You mean like each line is connected only to one capacitor?
Right.
Okay.
Right.
Okay. And those are just.
It was just a slow bit.
Okay. Okay.
And you should well, and it's more or less in scale because each wire here has a width about 100 nanometers, or give or take 200. And this guy is part of the millimeter, let's say 200 microns. So it's a factor of thousands of meters. That's why I draw it like that. So it's here.
And Q is just the number of charges.
Q.
Yes, Q.
Q is the Q is well, I should really write it here as operators, right?
Okay.
And Q is the charge which is conjugated to the phase.
Okay.
So it's dimensionless quantity. So for my purposes, today it will be just sufficient to think about it as these schematics and do not think about how you geometrically put these guys around. Now, so now if you do perturbation theory, which is sufficient for this purpose, for our purposes, then the fourth term is nothing but the, so let's recollect that phi squared average is nothing but 1 over Ej in the ground state. Sorry, in the state n is 1 over Ej h omega naught n plus 1 half. So half of the energy goes into Ej well, 2 pro. Yes. So that this 5/4 term therefore is with all the coefficients, you get very nice formula that it is 1/4, I think, EC n times n minus 1. So where is that's in the state n. So what it tells us that indeed there is nonlinear terms because the energies En is n plus 1 half h omega naught minus or so that is our nonlinear term. So, and you see that unfortunately in the coefficients work like that, that nonlinear term doesn't contain any other parameter but the charging energy. Why it is unfortunate? Because what I didn't explain you before is that this Q is counted with respect to some offset charge. The offset charge is just some random fields which are in your problem. And of course, not only we do not know it fluctuates and behaves in a very nasty and I will say even evil manner. So what we want is that our results do not depend on this offset charge, which is okay as long as we can regard phi as a U1 variable and not as a continuous variable and and forget about the periodicity. If we allow processes in which phase changes by 2 pi, then immediately this charge becomes important. If you wish, it's like a magnetic field. So what we cannot afford is that there are if we think about this cosine, what we cannot allow that there are transitions from one minimum to another minimum of the cosine. That completely destroys all coherence. So these transitions are extremely bad. Okay, so but if we do not allow these transitions, then it means that EC is much smaller than EJ. Because EC is like a mass in our problem. So 1 over mass in our problem. And EJ is potential, so in order to prevent these transitions over the barrier, we need that EC is much smaller than EJ. And therefore, the nonlinearity is always small. And that's the first part, the first step at which we start to lose our wonderful quality factor. So, in a sort of natural devices, people usually cheer, well, not always, but typical frequency that people prefer to work are somewhere around 5 gigahertz range. There is a reason for that, which I'll tell you about later. Why it is 5 is a sort of a sweet spot, and so and for the EC, one usually chooses around 200 megahertz. So that's, as you saw, times 2 pi. So you see immediately lost already a factor of 20. So, okay, but that's not the whole. Unfortunately, that's not the end. You continue to lose more and more. So now, what we want is to have some interaction between transmons, because each individual transmon is, of course, completely useless object. So what we want is some interaction between transmons, and as I will now explain you, this interaction between transmons is always much smaller than EC, and we know that it should be much smaller because the only thing that allows us to neglect higher levels and reduce the problem to trivial linear oscillator problem is this presence of the nonlinearity, and therefore we have to have interaction which is much smaller than EC, otherwise we are dead. So, and in fact, it's usually a factor of 10 smaller. So what we get is that the interaction is at around 20 megahertz. Typically, again, if you push it, maybe you can get 35, but you cannot really get much more than that. Otherwise, you start to get back to linear oscillator. Okay, and so as a result, what you see is that you lost now a few hundreds. And so what you thought was a very decent Q was becoming just a Q of 10 to 4 or about well, at least certainly less than 10 to 5. 10 to 5 will be too much. Because now we have really to divide the correct definition of the Q. Not this one, it's not this one, but it's really the interaction times the Q1. And this Q is sort of realistically 10 to 4, maybe when pushed is 10 to 5. Yeah,
sure. Just a question. So you told that linear problem is trivial. So do I understand correctly that you meant that actually any kind of physical problem you're actually interested in to model,
yeah.
It has some non-linearity inside, and thus you...
Yes,
okay.
if I want to reduce my problem just to spin, then I have to work at the time scales or frequency scales much smaller than the non-linearity. And that means that the interaction that I can allow between the qubits should be smaller than linearity. Otherwise, I start to admix all the states of the transmon above. So, and moreover, there is one more problem that I didn't want maybe to tell you, but in principle, it's really serious that if you start to occupy even a little level 2, 3, and so on, then these levels can decay very efficient. So you immediately admix very large decoherence. So these they are called doublons in the jargon. Let's say that doubly occupied levels. They are typically very dangerous. Okay. So now let's. So after we decided that we realized that our life is much worse than we thought, let's talk about what is the typical interaction, what is the interaction between transmon, and therefore, after all, what is the natural commutator? And that's actually the main part what I wanted to tell you today. So the most natural way to answer
How do you want to define why the parameters of the polynomial?
Well, no, I mean, T1 comes from the evil agents that you have, right, in your system. It's not directly related to the physical, to this circuit that, so since I need to, I will draw it again. So we have this trivial circuit, right? Josephson junction. So there is there is nothing about T1 and T2 in this circuit. The T1 and T2 is, if you wish, well, as if you had some additional normal resistance here, right? Well, that's a very, very crude and even wrong picture, but that's how you can think about it. There is some other degrees of freedom which were not written on the board at all. That gives you the decay and dephasing of the transport. So the one which I will discuss a little bit, something intrinsic, a bit later when we talk about redout, which is very important. And can we do something with air here? Because I think I am going to die.
Plus. Oh, the best we can do is open the window.
But outside is terrible.
Sorry, another question.
Yeah.
Just for me to how to think about the numbers, what is considered to be a good quality factor? I mean, obviously 10 to the power 5.
Yeah, it will come. It will come.
Okay.
It will come. I will explain why 10 to 5 is actually, even 10 to 5 is better. Maybe it's a good time. It's a good time to do it now. Just a second. That's indeed a very good question. So, before we discuss what is the interaction, which quality factor is I emphasize that I define the quality factor like none, not. Yeah.
Maybe you take another pencil which would be more visible. There is a lot of them.
You think they are different?
Yeah, some of them
I think they were on Friday.
Yeah.
So, so what we want is that if we have some sort of big system, right, with many qubits, something here, right, that we represent as spins and so on. What we want is that due to the interaction, we form some coherent state in the system. So clearly, if the system has a size L, then clearly time, and the characteristic time is 1 over u, we need time which is 1 over u time L, just to spread the coherence through the system, at least, because it cannot propagate faster. If anything, ideally we would like to have much larger than that. Because if we want to study a non-trivial process, probably it doesn't propagate immediately. It just needs to establish some coherence.
Now t is like the time of our coherence.
Yeah. So we need
Okay.
we need that the system lives
Yes.
this amount of time. However, now, of course, T should be less than T1, because if each qubit decays, then we do not get anything interesting at all. But in fact, for most, if we want to form a non-trivial coherent state of 4 qubits, it's worse. Because usually, if we lose 1 qubit, if we have just single Q1 process somewhere in the system, so that some of these spins suddenly flips, that destroys interesting states. Non-trivial states. And what does it mean? It means that not a single qubit has to experience this T1 process, and therefore the effective T1 of a big system is 1/n times shorter than T1 of individual qubit. In this case, you see that if we talk about something in which we can hope to obtain interesting results, that is systems with, well, let's say, 100 to 200 qubits, then we have a condition that T1 times U should be much larger than this factor of L if it is two-dimensional system, which is 1/2, and then we have 3/2 here because of this factor of N. So you see that, and that is sort of borderline condition. So that you see that for N, which is a few hundreds, we are barely making it. So Q is Q which is 10 to 3 is not sufficient. And then, well, then you decide what is sufficient. 10 to 4 maybe, 10 to 5 probably. So we are really operating on a very marginal. Okay, so that is why the numbers. Yeah.
Just another question. So we're not talking about ground states, right?
Well, we're talking about yes. We are talking about ground state will be worse because we want to prepare because in order to prepare the ground state, you want to get rid of the low energy excitations. Sort of cool, if you wish, cool your system down so that the low energy excitations disappear, and that takes additional long time.
I mean, I would expect that even if some spins occasionally flipped, and the system gathers like bigger energy, then the probabilities for it to flip back are much bigger. So okay, probably some of them from time to time they flip, but they go back, no?
Yeah, what you want to tell me is that there could be problems for which small density of quasi-particles is not such a big problem.
Just like that.
Yeah, but these systems are not so interesting because you can also simulate them efficiently classically.
Okay.
So that's, if you want something interesting, it's fragile. And it's fragile.
Yeah, we're here. Okay. Thank you.
Very, yes. Okay, so that's why all our problems. Now comes the next subject, which is what I said, that there is interaction between transmons that cannot be larger than 20 megahertz, well, for typical numbers. So how this interaction between transmons is implemented, and therefore what is the nature? Okay, so the easiest thing that one can imagine is that one simply couple the transmons with the capacitor. That is a perfectly good thing to do if it were not for the fact that this is, of course, not switchable interaction, and therefore you cannot really do much about it. You just, it's always there, and so which is extremely inconvenient. So what we want is really the way to switch this interaction on and off, otherwise our system is not controllable. So there are few ways to do that. So the way that we use at Google is that instead of the capacitive interaction, we have another sort of transmon, which we call coupler. And I will explain that it looks like it's just another transform, but it's not. And I will explain in a second why. So, although physically it looks very similar to the qubit transform, the difference between them is that the frequency of this coupler is much larger, well, not much, significantly larger than the frequency of the qubit. So, so the process in which we have, so the interaction between the two is H interaction is let's say call it G. I don't want to introduce too many letters because I will not need them in a second. So, in physical terms, the interaction is given by the capacitive well, you can imagine that we have something like this. For the capacitance, where C naught is the capacitance of the transform, and C is the coupling capacitance. So when we invert this capacitance matrix, we get here Q C minus 1 right? And so as a result, so at the end of the day, we get the interaction between the yes, so that's so of course Q as operator is a non-zero matrix elements between states 0 and 1. States 0 and 1. And so when we combine this, what is this? Q1 is some coefficient, I hope that I remember it correctly, square root of EC over EJ. So at the end of the day, what we have here is the sigma x operator, which acts on a qubit 1, sigma x operator, which acts on qubit on coupler, and the coefficient in front of them, which is before I made a mistake to denote it by U. Okay, let me call it sorry about. So that's the effective Hamiltonian of the qubit coupler system. But as I said, that you have also the terms which are okay. So now what is the main effect of this Hamiltonian? Because don't forget that our qubit frequencies are enormous. Much larger than U, because remember that U should be smaller than the unharmonicity, and therefore unharmonicity is much smaller than the qubit frequency. So these frequencies are huge compared even omega q minus omega c, or backwards minus plus is much larger than V. So the only process which is relevant for this Hamiltonian is a process in which we flip the one qubit up, another qubit down, so to or the coupler down, plus, let's say, the same for the so that's the only relevant processes that we have. Moreover, if our coupler frequency is sufficiently away, even this process can be taken into the account in the perturbation theory, and we get the final result that effective Hamiltonian is just G sigma 1 plus sigma 2 minus plus sigma 1 minus sigma 2 plus, where G is U squared divided by, how we denoted omega coupler minus omega cube up to a factor of 2, which I don't know. So now, so that is our final result. The effective Hamiltonian is this, and that tells us how we can actually control the interaction. We control the interaction by moving the coupler frequency up and down. And now the sign. Let's discuss the signs, which are of course very confusing always. So here, this interaction appears in the second order of perturbation theory, therefore it has sign minus. That is, from the physics point of view, in terms of physics language, what we have is that all the spins want to point in the same direction in xy plane. Good. However, there is one thing that we forgot about when we discussed it. There is also direct charge coupling, because these are real physical objects. So there is some charge interaction, and this charge interaction is
Sorry.
Yes, absolutely.
Yeah, just to make sure.
Yeah.
So the claim is that you can actually control the frequency of the coupling. Of the coupler.
Yes.
Okay? And
how it's done is that, that in fact all this, when I was drawing the junctions, I should really draw them as in this architecture. I should really draw them like that as a controllable. And in fact, the definition of the controllable junction is that instead of one junction, you have two junctions and the flux which penetrates them, so that they either add coherently or incoherently. It's really, you replace each junction by the squid loop. And there is a little magnet, not a magnet really, a little coil sitting here, which creates a flux acting on each loop.
So this is for junction or for junction?
No, each junction is in fact, so okay, in my little cartoon here, what we do, in fact, is this.
Okay. Okay.
So that this is one junction and this is another.
Yeah.
And there is a flux here. So that's how to, to do it geometrically. I mean, how to. It's different people do it differently. Yes.
I mean, so in principle, you can control in this manner any kind of frequency of any qubit, but you don't need it. Okay.
No. In this architecture, at least this is Google architecture, we control the frequency of all qubits and all couples.
Mm-hmm.
And that is on paper nice. In reality, it's a very difficult problem because when the number of qubits increase, the number of control wires increases enormously.
Mm-hmm.
Yeah, and another amount of control electronics also increases enormously. As I was here, I want to say that because of the presence of the parasitic, if you wish, coupling between the qubits, there is a term here which is G naught, which is small. It's normally it's much smaller than this guy, but it's of opposite sign. And that trivial remark allowed Google people in fact, I should really put the praise on the person who noticed that, and on Charles Neal, who's invented all this architecture, that it is possible if you move copper very, very far away, not in this work regime where this is relatively small, so that is when you have the interaction of the order of 20 megahertz corresponds in this case to the difference in the frequencies of the order of 1 gigahertz. But if you move this frequency very far away, let's say 10 gigahertz away, then the G is equal to 0 because it's two terms cancel. And that was observation and this, that allowed Charles to make this architecture, and that was very, very successfully used for a number of projects. Okay, so good. So that is this most standard, not the most standard, that's a thing that was implemented many, many times, not only by Google, but by other groups. But it has, from the viewpoint of simulations of interesting systems, it has a very important drawback. Namely, the interaction that you can get has only this sign, which is ferromagnetic, and yes, and we have one more unpleasant problem. Look, in order to have significant interaction in this setup, we should have not negligible capacitance between the qubits, because I didn't write it, but now maybe it's time to recollect it. What is the formula here for the so this U, let me write it without doing this algebra for you. Something of this sort. So you see that we should, if we want to have significant U, so that eventually our G is not negligible, we need to have a significant value of the capacitance. And why it's a problem? It's a problem because capacitance cannot be larger than the capacitance of a transform. Trivially, right? And this is not a problem if we just have two qubits. But now imagine that we have array. Array means that we have this little big couple, one transform with another transform here, and with another transform here, and with another transform here, and with another transform here. You see that all these capacitors, in fact, add to the capacitor of the transform. As a result, if you have coordination number Z, then you can clearly see that C should be smaller, and in fact significantly smaller than C naught over Z. And so that means that we could, or Google could get through with Z equals 4. But if you just start to put the numbers, then Z equals 6 is already impossible. You just get so much parasitic capacitance which contribute to the capacitance of your transform that you have very weak interaction. So that large coordination numbers are impossible. And that's why IBM always uses 3 for coordination numbers, or actually 2.5.
What is 2.5?
Oh, they have sometimes 2 or sometimes 3. It's complicated array, so that on average it's 2.5.
They have to think about that, like maximum number of qubits I can couple.
Yeah.
To.
Yes. And that, of course, and then if you go back to what our previous discussion, what is a good quality factor? You remember that I said that the quantum information should be able to propagate through the whole system. But the less is coordination number, the more inefficient is this propagation. So in principle, if you could have a very large coordination number, then you would spread the quantum information immediately. For very small, it takes many steps. So what you lose here is not innocent. You lose a lot if you decrease the coordination number. Yeah.
You mean just because like this effective size of the system will be smaller, or because of some kind of interferential effect, the propagation will be faster?
I mean that how many steps you need to take to get to the every cube.
So just the size of the system.
Right.
Okay.
Well, you can say that go. Yeah.
Mm.
Good. All right. So this is our system, but as I said, it's not. It has these many problems, for especially for simulating interesting physics questions, namely the sign of the interaction and the fact that we are limited with the coordination number 4. Well, 3, of course, people do, but it's even less interesting. Okay, so what else can one do? And especially to study some interesting physics problems. Another option, and that actually we can use even our system for that, is a fold. So let's forget about our desire to couple, to have large coordination number. Okay, so suppose we now do completely different thing. We choose our frequencies of the transforms so that they all be sufficiently different of the qubits. So that they're all sufficiently different from each other. So that so they're all different, and therefore the interaction that we happily derived before does nothing. So that the difference delta omega is much larger than g. So this interaction doesn't lead to any exchange because they all have different frequencies. Yeah.
Sorry, the indices, like the Q index?
Yes, Q is just to say that it's a qubit. Maybe I should.
So this is not an index. This is just like
Yeah.
Okay.
Just to remind that it was a qubit. Because I will now talk about coupler for a second.
They are just the same sigmas.
Yeah.
Z and sigma plus.
Yeah.
Okay.
Yes.
So
So
that's a bit confusing.
okay, let's
Erase. Thanks.
let's erase this. Although I will maybe need some different notation in a second. So very good. So that does nothing. Well, it's a bit of a simplification. And actually that's a quite interesting story in itself, this simplification. Because, of course, let's discuss this purely theoretical problem for a second. So suppose I have one-dimensional chain of spins and one dimensional just for simplicity, And here I have fields in the direction, which is my frequencies. These frequencies are different. However, I cannot have them all different, right? Because somewhere very far, I will always find the field which is almost equal to the field on a given site, right? Because, well, all very, very close. And therefore, one should worry. Yes. Yeah, yeah.
You mean that your transform is actually squid and your field is...
No, yeah, so my field, I can forget now about that it was a squid, oscillator, I just say it's just a spin.
Yes, I mean just the H is the same as omega.
Right.
Okay.
I just want to formulate it in terms of the physics problem, yeah. So look, I have some spurious resonances. Why is there bad? Because even very weak yes.
I'm so sorry, but I'm a little bit confused. You said that you have full control over the frequencies, so in principle you can make them as different as you want. So what?
Well, I cannot move them to 100 gigahertz, right? I can fine tune them.
Yeah.
But eventually I will. That's exactly the question that I want to formulate. So, what is the best choice of my H?
Okay.
So that these spurious resonances are as innocent as possible.
Yeah, okay,
so that I do not have uncontrolled or transfer of quantum information by large distances. What is known as, in normal physics, is known as mode conductivity. So I want, this is a process that I want to avoid. And so I have to ask what the best configuration of the fields best choice. That I do not have, if I do sort of a naive thing, that is, of course, a naive thing would be to put the fields, let me draw the fields. So let's say H is some H naught, which is my general frequency, plus delta H, and delta H as a, I put here minus, plus, and so on. And so if I do something like that, it's clearly bad, right? Because just these two become equal. And in the second order perturbation theory, I start to get resonance. So I have to be more creative than that. So if I just take random H, well, then what I find is that a typical wave function of this system, which is characterized by the what's known as participation. This participation ratio tells us that if the wave function is very well localized, that we want, is 1. And if it is, so maybe I should, and if it is delocalized, it's very small, then if we plot the distribution function of this P, then you find out that there is always, well, 1 over, so that we can look clearly at the small values. Then there is always some, of course there is a bulk, which is 1, but there is some unpleasant tail here, which tells us that sometimes we find the resonance far away. So we need to come up with a clear, with a nice way to distribute these fields so that to avoid this problem. Yes.
Sorry about the plot. So y-axis is
Y-axis is p, right? We have many wave functions, right?
Okay, so
Or 1 over p to be exact. So that
1 over p is
so 1 over p is the volume
the volume
of the wave function.
Okay. And p is, and y-axis is just probability.
Yes. Probability. Well, sorry, I don't know how to draw a Gaussian p.
Okay.
Okay.
Yeah. Okay.
So what we want is that there is no text. That is, there is no wave function that somehow sneaks out very far.
Okay.
And if you do something naive, like say it's random and so on, you always get some of them. Yes.
What do you mean by participation ratio for many-body problem?
Well, let's forget that it's many-body. Let's study linear problem.
Okay.
So in fact, for one-dimensional problems, there is a nice solution of that, which is the following: let's represent each number I in a binary notation. 0, 1, 1. And then let's construct let's put the field, which is the sum over the 1 over 2 to k. Bk is this once. The point is that in other words, what we do in this way, we start with this periodic modulation that we discussed before, and then we add to it further harmonics. That is, we shift this, let's say, up, this we shift slightly, let's say, also down. This we shift down, and so on and so forth. So we add more and more harmonics, which corresponds to the binary representation of this number. In other words, the fields which are identical correspond to, very close, correspond to the numbers which are very close in p-adic metric. If you know what is p-adic metric, okay, then good luck. No, there are two, there are two metrics that you can introduce on real numbers. One is Archimedes, and another is p-adic. P-adic metric is the following, just a second. It's funny, although it's not so easy. P-adic metric is the following: the distance between two numbers, p, is 1 over 2k, where 2k is the maximal power of 2 that divides I minus j. In other words, in this metric, the numbers which are divisible by very large powers of 2, well, p generally, but equal to, are very close. And that's very good for this type of problem, because if they are very far in normal space, they are very close in terms of this h. And it's unique correspondence. So, unfortunately, I don't know such a beautiful construction for the two-dimensional problem. Well, I can imagine some choices, but not so beautiful as this p-adic construction. But anyway, at least it's possible with some work to ensure that indeed this naive conclusion that in this Hamiltonian we have very localized states is correct. Okay. Now, but so far what we achieved after all this work is that we have interaction and nothing happens, which is not exactly what we want, right? It's sort of opposite. Now, so how we now switch on the interaction? And that is the whole point. So let me erase here. This we can erase. Now, instead of this, we write the G with some G naught, which we decided is irrelevant, plus G1 times cosine omega p. So, so we modulate our coupling. So we can imagine that we in fact control our coupler that produce this interaction to begin with. We can control it at some frequency, not statically, but at some frequency omega. Now, we choose, the most important thing is that we choose this omega to be equal to the difference between neighboring qubits. And here, as you will see in a second, the phase will be crucial. Because the fact that not only we have the, sorry, not only plus, I put phase in the wrong place, plus phase. So now what happens is that in principle, we now have a resonance process in which the one qubit goes, let's say qubit I goes from state 0 to state 1. It takes this takes energy omega I. Another qubit goes from 1 to 0, and it takes energy omega I plus E. And the difference between these two energies is supplied by this interaction. So now how to do that mathematically? Mathematically we go into the rotating wave approximation in which we rotate each qubit by its frequency I, by frequency omega I, and then in this new frame, what we get is that this interaction loses the time dependence, and we get simply sigma. Well, there is no sigma I term, sigma z terms at all for our qubits, but the term, this one, becomes the interaction you see that here the phase is true. The phase doesn't disappear because if you mathematically it happens like that. The cosine you write as exponential of I omega t plus I pi plus of course Hermitian conjugate, and only the correct sign of I after you go to rotating frame disappears. And the other one we can throw it. So
once again, we use the fact that omega I is much bigger than any other relevant.
right. So not only omega I, but also the difference. Unfortunately, not only omega I is much larger than J, but also all these differences that we just discussed, that omega I minus omega I plus E, is also much larger than J.
So they're of the same order?
Well, optimistic.
Oh, so rotating
So
approximation is very
no, the problem is that, well, physically, we can, if we have sort of base frequency, let's say 5, 6, whatever gigahertz, we cannot have them different by 5 or 6. We have 1 or 2 at most. So that, so there is, we always lose a factor of 5 or something like that here. So in this way, but you see what we achieved is actually quite interesting for physical applications because we now have a frustration. Our interaction is no longer necessarily ferromagnetic or antiferromagnetic. We can have any frustration that we want in this way.
You mean by controlling the phase?
By controlling the phase, yeah. Moreover, if we are really impudent, we can do slightly more. We can put here G2 cosine of another frequency, and I'll, so let's say it was omega 1, and this is omega 2 plus its own phase. And we can choose omega 2. So omega 1 we chose as a difference, and omega 2 we can principally choose as a sum. So what that means is that in this case, we also will get the term which is up in rotating wave approximation, normally forbids us to having a term and now what we achieve, because we now have a sum of sigma plus, sigma minus, and sigma plus, sigma plus, which means that we can engineer interaction.
Sorry. I completely missed the point. What moment we get this term sigma?
Oh, because you see, omega 2 is now the sum of the frequencies. So we now allowed the process in which both qubits flip up.
Because we're like driving it.
We're driving with the sum instead of the difference. Of course, just drive.
Okay. So we add additional
Yes.
omega 2. Oh. Sorry. Yeah, thank you. Yeah.
So, and of course, just to have J2 instead of J1 doesn't buy us anything because we can always change this notation, sigma plus to sigma minus. However, if we have both, then we can get interaction. Let's say if we just have the J1 equal J2, then it's identical. So as to say that we have interaction which is sigma x, sigma x. Or we can have sigma y, sigma y. So in principle, in this way, we can design any, well, not any, but this type of non-trivial interactions which are not possible to get by sort of conventional spin systems.
You mean it is long range interaction?
It's not well.
No, several lattice.
Well, long range is a separate story. That so far as I said, if I just have a coupler and I modulate the coupler, then what I get is, of course, the interaction between the qubits which are connected by the coupler and not anything else. But you're right that if I'm even more clever and I put here sort of long resonator in my system, then I can have a long range interaction of this sort. But I need, of course, physically to couple them by some line.
But you also mentioned that the energy differences, basic energy differences, would be such that you have near resonance between some long separated.
Yes, well, that's completely in my hands, whatever I want.
which means that at higher order of interaction you will get very
Yes.
also count.
Right, yes. Yes.
Just a stupid question. How does qubit practically distinguishes this phi? I mean, how should I think about this physically? How, I mean, because the moment of time when I switch on this interaction is more or less arbitrary. How does the qubit feels this phi? I mean,
Right. Because what it feels is a difference.
Okay, well, this is much better because if you remove G2,
Yeah.
probably this amounts to the definition of sigma minus.
Yes.
Okay, then maybe less stupid question is, so when you do this, first of all, already at the level of this model, you have some kind of noise that you introduce in the system, which, judging by the discussion that was before, might swell things significantly. And moreover, by driving, let's say, coupler at one point, you then unavoidably kind of passively drive all other qubits with this.
Again from the beginning.
Well, my basic statement is this: when you drive your coupler with this with your current that you which you launch through this contour, where you don't just influence this very coupler that we are interested in, but also all other loops in the system that you have, and in this sense, you kind of introduce certain.
Why I'm not driving my coupler when I want to?
No, you of course you are driving your coupler, but also, well, because electrodynamics is not local, you drive.
It is
also.
local.
Ah, okay.
No, this is how to design the ground planes and how to screen the interaction. That you are right that if you want to tell me that there is some parasitic crosstalk, yes, there is, but it's well, it's not such a big deal. It's really only to the next nearest neighbors. So and not well, and even at this level, it's like 10 to minus 3. So well, that should be the least of our. That's actually the least of our worries. There are many much more important things to be afraid of.
Can I ask one?
Yeah, sure.
Example from the previous static argument. Why wouldn't you do some kind of a incremental range?
Oh, it works. I tried.
You tried.
Yes, I tried. Actually, it was.
Why we are doing this instead of some incremental range?
You're right. So, I don't know what people know about it because definitely it's a big problem for IBM architecture, but they don't discuss it. So, as always with them. And so what I don't, like, we can only guess what they do, right? But just as a little exercise, I tried different choice of frequencies, random, incrementally that you suggested, and the one that I presented was by far the best.
With an empirical observation or
Right, yeah, you are completely right. That was my first idea to try. Yes, and so more on this point of crosstalk and so on. So you realize that in the rotating wave approximation, what I am doing, I am keeping after I go to rotating wave, I am keeping these terms and I throw away the terms which are proportional to 2i, let's say, omega times sigma plus sigma minus. So what I want is that these terms are sufficiently smaller that I can ignore them. And that means, of course, implies that this whole interaction should be small enough so not to lead to any harmonic generation and so on. So the result is, at least for this implementation, I'm not sure how general is the statement, that G is realistically even smaller. Then I said that for, before that for static coupling we can achieve 20, maybe even 30 megahertz, and here we can, well, I will not hope then more than 10 at least. At least, well, as far as I know, if you try to push it more, then you start to generate these higher harmonics, and these terms become relevant. You start to get stray populations and so on. So although this allows us to get very interesting interaction, the value of the interaction is even smaller than what we get statically. Not much, factor of 2 probably, but always worse. Yes. Okay, so, well, I want to discuss readout, but I think that I don't have time for that, so I basically stop now and leave readout for the next lesson. If you have questions, please ask me.
Why was 5 gigahertz the sweet spot?
Okay. So on one hand, well, our temperature is not zero, right? So realistically, well, nominally in the cryostat the temperature is 20 millikelvin, which translates into what is this?
500 megahertz.
500 megahertz. Thank you. So, but in reality, the population of the qubits shows that the actual temperature is 100 millikelvin itself. So that leads to a population of the qubit at 5 gigahertz about 1%, which is already bad. So people try to decrease the frequency even more, but then one needs to engineer a very efficient cooling. For cooling, not in terms of the cooling as a temperature, but as a reset of the qubit. So that's one thing. And on the other hand, why not to move higher up? Part of the problem is that we need to have also readout that I will discuss next time. And the readout frequencies are better, and as I will explain why. Readout frequencies has to be higher than the qubit frequencies, not lower. So now, how high we can move them? Well, the electronics becomes prohibitively expensive if we go much above 10 gigahertz. Well, 20 is bytes.
Yes.
So well, that's why we can sort of negotiate not 5 but 7, and so Nakamura uses 8, but it's not that. So people who go to lower frequencies, they have problems with the reset. It is possible, but it opens another kind of work. So, well, that's.
So to go higher is more practical limitations like...
Yeah, it's purely practical, right? It's not, yes, so there is also a very interesting question if there is something in the spectrum of the environment which is, which makes us to prefer 5 versus 3 or versus 8. But it seems that there is not. Although there were contradictory claims about what is the spectrum of the environment, and Clara will talk about it hopefully when she comes tomorrow. Yeah.
Speaking about environment, so in your system all interactions was local, this resonance, the field appearing higher over
Yes.
return to
Yeah.
local interaction, but could environment produce some local interaction? Does it affect?
Oh, my God. Yes, yes. So, and that is, yes, so when you make a big system, you start to suffer from the fact that the velocity of light is finite, right? It's not infinitely. So if you make a system which contains, let's say, a few hundred qubits, it's basically this size, right? And for this size, the frequency is already in gigahertz range. So you have some modes in your package that qubit talk to. And you have to be very careful to make sure that these modes do not present a problem. Because yes, you can easily imagine that the qubit interacts with one of these microwave modes in this package, and then interacts with another qubit, and you have no idea that it happened because you didn't know about the existence of this mode. That's a big problem. You need to do very complicated microwave engineering when you go to large sizes. And that is not a trivial problem.
You have this, for each cube you have 4 areas attached?
All right, four legs. No, in fact, 5. To be honest, 5, because there is also redoubt.
These are 2 meters long, and do they show collective excitation?
No, this is small, right? These legs are small, so there are no.
Yeah, right now.
Yeah, so and everything is supposed to be screened, so that's purely local interaction. Well, how well you are screened is. So ideally, what you want to screen by the flip chip, right? But that brings another problem, which is stress that we discussed. So, and if you make it everything in the vacuum, then you are hit by the modes in the vacuum. Yes.
And how constrained are you in parameters? I mean, in the parameter space?
Well, you know, in this system that we have now, Google, which is this static interaction, you are completely constrained. You cannot move at all. You are hit on all sides from different considerations. You have to change a lot the architecture in order to get rid of these constraints. But so in this original Charles design, you cannot do anything.
Right, so
he was very lucky that it works. It barely works.
So you need to work on the environment.
Yeah. Okay. Thank you.